The International Doctorate School on Particle Astrophysics and Cosmology, that is a network with several countries, essentially from the southwest of Europe. And Professor Luis Álvarez Gómez has been invited in the context of this event. So I think he doesn't need the presentation, but nevertheless, let's just comment. Luis was born in Madrid. He studied at the Autonomous University of Madrid, and in '78 you go to make the PhD at one of the places where supergravity was discovered 2 years before, and his advisor was one of them, Friedman. And after that, his career goes to Harvard through several positions, and later on professor at Boston. And after that, Boston University, and after that, he became established in the theory department.
Sorry.
No, department.
Then one division, then it was nothing, and then it was the department.
At CERN, and he was director for several times, and also deputy director,
yep.
Almost forever. No?
For 2 years. It was my cross.
So, and we're going to talk about this provocative title, Relevance in Goldstone Theorem.
Thank you, Kiko. Can you hear me? Anyway, I didn't know that this was a colloquium including experimentalists. So some of the transparency may contain a few formulas, so what I'll do is I'll start with blah, 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 pass them very fast. The issue is try to think about some of the ideas, which I think are kind of interesting. Lately I've been doing number theory. In other words, I'm just trying to adjust budgets. So I'm a little rusty in getting into scientific discussion, so have pity on me. Don't ask questions that are very difficult. And I hope that it's only going to last for an hour. So even if there are many formulas, it should not be too painful. Now, when you look at the modern quantum field theory textbooks, it seems that there's always about 2 pages where Goldstone's theorem is proved, and then it seems that there are all kinds of conditions and so on and so forth. Everything is clear. And the problem is that sometimes it's like throwing the baby with the bathwater, because if you begin to analyze some of the conditions and some of the details that are hidden behind the proof, you find that there are many loopholes, and there are many cases in nature, including even relativistic theories, where somehow the standard version of Goldstone's theorem doesn't work. I'll try to convince you that, in fact, there's still a lot of room to understand symmetry breaking in physics, and not necessarily in relativistic quantum field theory, and that some of them appear even in theories that have relativistic invariance. But in some contexts, like for example, theories which are conformally invariant, theories that have some global symmetries, theories where you can try to construct the states with very large angular momentum, or state with a lot of charge, close to this semi-classical limit, the WKB approximation. And it's very interesting that a whole new phenomenology, at least theoretical phenomenology, appears that is also connected with applications in condensed matter physics. Condensed matter physics still has not finished or ended surprising us with new materials, and therefore with new phase transitions and new ways of implementing or breaking symmetries. So it's kind of interesting that once you begin to understand how Lorentz symmetry breaks, and it's not implementing the ground state, a whole new phenomenology appears. So this is more or less the story of how I got into this. A few years ago, those people, Hellerman, Orlando, Reffert, and Watanabe, were studying in detail the behavior of the Wilson-Fisher fixed point. This is one of the basic objects that are studied in the normalization group. This is essentially like a theory which contains an O2 symmetry, just simple U1 rotation, global charge. And what they were trying to look for is for what you might call conformal fixed points. In other words, they're looking for places or values of the couplings describing a second order phase transition. Okay? In the language of field theory, this is described always by looking at fixed points of the normalization group. Okay? But this is, of course, something that you cannot compute analytically most of the time. Because this is the case, as you will see later, of Hamiltonians, where the coupling constants are order 1. So you cannot expand in anything. That's where, unfortunately, you would like to have fixed points, which describe the ultraviolet or the infrared in your theory, where the coupling constants are small, and therefore you can do some perturbative expansion for some observables. Unfortunately, nature is not kind to us, and most of the time, the theory that approximately describes the fixed points do not have an expansion parameter. So we have to invent one. In QCD, for example, what you do sometimes is to expand in the number of colors. We assume that the number of colors is not 3, it's n, and then you try to make sense of QCD expanding in 1 over n. And frequently, at least from the qualitative point of view, you get fairly interesting and useful information. Well, in this context, what we found out, or these people started finding out, is that since you have a charge, you have a conserved quantity, what happens if you begin to study how that big, you cannot study the whole theory or the whole Hilbert space, but what can we say about the states that have a large amount of charge? And what we found, remarkably, is that there is a well-defined expansion in 1 over q. And that expansion in 1 over q, because some terms you have to fit to experiment to Monte Carlo simulations, but some terms we can compute analytically, and they fit the experiment, as you will see later, with unreasonable precision. So now this is an interesting new window to look at some sectors of some of these theories that have infrared or ultraviolet fixed points that you can access semi-analytically. Okay? So this is essentially what we're trying to do, and as you will see, well, this led us essentially to the study of novel ways of understanding symmetric breaking patterns, but of course, this is going to lead us, as you will see, into the appearance of non-relativistic behavior, a very special type of non-relativistic behavior inside ordinary quantum field theories, but again, giving us some way of computing things that are not accessible to a standard perturbation theory. Many of the arguments that I will be discussing today are very heuristic, but the interesting thing is that they agree quite well with some Monte Carlo simulations, so there's been some work after what we were doing, and in fact, it's kind of encouraging. Not that we can solve any theory at strong coupling, but in theory that have some global charges that are conserved, there are sectors of the Hilbert space that can be accessible or can be accessed semi-analytically. Well, just a reminder, to start with a reminder, for the first few transparencies, first few slides, everybody will understand, hopefully, because it's not just general blah blah. I mean, this is the kind of thing that every time you start looking at a book in normalization group techniques or the elementary quantum field theory and so on, you have this thing which is descriptive, many pictures, a lot of blah blah, and then little by little we'll enter into murky waters. One thing that we've learned over the last many years, but certainly it's become quite important in the last decade, is somehow the relevance and the importance that conformal field theories play in quantum field theory. The conformal field theories, if you want to think about them in the simplest possible form, are theories that are invariant under scale transformations. Like when you look at a fractal, the fractals, every so many steps, you recover the same structure. Well, fortunately, quantum field theory, since we have translational invariance and rotational invariance and so on, somehow what we found so far is that the realization of scale invariance is based on fixed points. There's no proof of that. Something which remains to be proved. Why in quantum field theory that is Lorentz invariant and local, the only long-term behavior or long-scale behavior or short-scale behavior is always a fixed point. It's not a limit cycle, stress attractor, the Lorentz butterfly. That's something that we have not found in quantum field theory, but in 4 dimensions we still don't have a theorem. In 2 dimensions we know that we can prove it. In 4 dimensions it's a little bit more complicated and we still have to have a proof. But in any case, if we make that assumption, somehow the fixed points of the normalization group are important in our description of the infrared or ultraviolet properties, but also connect quantum field theory in continuous systems with critical phenomena. This is why Wilson and Wilson's technique have been so fruitful in applications to these things. In the string theory or quantum gravity is also one of the guiding principles. In fact, string theory and the critical dimensions and all this type of things is based precisely on the fact that the microscopic theory has to be scale invariant. And it's thanks to this scale invariance in that particular formulation that we learn a large amount of stuff from string theory. Now, one thing that I would like to say is that somehow, beyond 2 dimensions, where we have what is called samological free theorem, which somehow you can prove, again, with locality, relativistic invariance, and so on, that somehow the normalization group is monotonic. It's a gradient flow that is monotonic, and therefore, the way you flow in that particular space is relatively simple. In 4 dimensions, that's not true. 4 dimensions, the space of all field theories is extraordinarily hostile. In fact, to describe most Hamiltonians or most theories, you need an infinite number of operators. So the only place where you can get some, some rest is when you are close to a conformal fixed point, where somehow you are described by the fixed point theory and a few perturbations around it. Okay? So this is the way we access at least special field theories by looking precisely for these different fixed points and then looking at small perturbations and trying to see if we can flow from one fixed point to another. But in any case, this is some kind of general knowledge that we've had for quite a number of time. Now, as I was trying to say before, is that the problem with most conformal field theories is that there are no small parameters, generically. People sometimes say, well, let's do duality. You go from coupling constant G to 1 over G. But if G is equal to 1, then G at 1 over G is also 1. So there's no magic can expand. Now, of course, eventually, we have to rely on lattice computations, Monte Carlo simulations of quantum field theories, gauge or without gauge symmetries. And lately, there's been some reincarnation of the bootstrap approach, that some of you might know, and if you don't, it's just a name, which somehow is a set of consistency conditions that you can write down to be able to compute or to constrain the masses or the anomalous dimensions and the 3-point functions, in other words, the interaction vertices in the theory. And out of this, you can construct any correlation function in that particular theory, that is in principle. The rule that most of this work is always numeric. So the questions are relatively complex, so you make a few assumptions of self-consistency, and then you end up getting into some of these bootstrap methods. So what I was trying to say is that, there are ways of doing bootstrap, but let's try to forget about the bootstrap now and try to see if we can find some of the techniques or some of the methods that give us some insight into some of these non-trivial fixed points, but looking at them from a different point of view. And this is the one I was trying to say regarding large Jersey expansions. Now, before I get into some examples of this computation, which are relatively complex, so I'll try to skip it very fast. I don't want to look at the details. Anyway, put the details so that you show that I've been doing some work. So that you see that I can still do some integrals and do some computations. But in relativistic local quantum field theory, what we normally are told is that we have the Wigner-Weil or the Nabu-Goldstone realization of the global symmetries. And the general properties in that case are relatively well understood. In fact, in the non-relativistic context, the symmetry breaking patterns, as I was trying to say before, are rather complex. We still don't have a complete picture of what goes on. So what we are doing now is something, as I was trying to say, is an intermediate. We don't want to have the complete freedom of looking at generic non-relativistic field theories, because that's a mess. We still haven't been able to put some order, even the condensed people, as I say, keep discovering new materials and new patterns of symmetry breaking. But we can start with a theory that deep down is relativistic and local. But when you look at it to the infrared, to some sector of the Hilbert space, it is described by an effective field theory that is non-relativistic. So there is more control on the type of operators, the type of excitations that describe the infrared in a particular theory. So let's remind ourselves of some of what everybody should know about Goldstone theorem. The first thing I'd like to maybe to remind you, or tell you didn't know about it, is Goldman's theorem. Goldman's theorem. This is from 1964-65. I think very few people were born at that time in this audience, so it's kind of ancient history. But the interesting thing is that if you have local unitary quantum field theory, I don't even tell you which one it is. It's unnecessary. Goldman's theorem tells you that the symmetries of the vacuum are the symmetries of the world. In other words, you give me a current, relativistic current J mu, J naught, J I compute this charge Q. It doesn't have to be conserved then. Just take this object. If the ground state is annihilated by this symmetry, you can prove rigorously that then the current is conserved and that Q conjugates with a Hamiltonian. It's not used anywhere. This is an extremely powerful consequence of locality, relativistic invariance, and unitarity. You break any of those three, and the theorem goes. But this is the basis of the simplicity of symmetry realizations in relativistic theories. Is it clear? This is false in the non-relativistic case, for example. Okay? So let's try to remind ourselves, this has many formulas, but these are simple. If we try to understand the relativistic and the non-relativistic case, let me try to do geonotic construction. Let's look at the simplest possible example of a relativistic Goldstone boson, and the simplest possible example in the non-relativistic context. So it's just one slide each. The simplest example, obviously, is to look at a free scalar field, real, and the symmetry, of course, is just a shift, phi to phi plus a constant. This more or less describes, in low energies, any Goldstone boson. Because if any Goldstone boson is associated to some rotational symmetry, I can always fix the modulus of whichever field is rotating to its vacuum expectation value, and then I have the phase that will be moving by the symmetry. So, at low energies and long distances, this is not such a bad approximation for the small fluctuations around the ground state. Okay? Because we can always beef it up and make it more complex and put all you like. But essentially, this contains the roots of all the good properties of Goldstone's theorem. For example, let's prove that Goldstone's theorem only works in infinite volume. Well, we'll prove it in this transparency. Now, if I have the charge, of course, in this case, is just the derivative of phi. And therefore, well, this is the current. The charge Q is the integral of phi dot, which is the canonical momentum. And of course, it is the canonical conjugate of the phi, of the field phi. You have IQ commutated with phi is equal to 1. And of course, this charge moves the field or shifts it by a constant, because that is psi. Is that clear? When you quantize this theory, what you do? Well, you simply look at, in this case, the solutions to box phi equal to 0. These are plane waves. But we're in finite volume and with periodic boundary conditions. Then I still have to include two modes, the constant mode and the mode that is linear in T. These are perfectly well-defined solutions to the wave equation. And now, let's canonically quantize. Well, of course, the usual creation and annihilation operators will do the usual thing, but the important thing is that if L is the size of the box, we have these additional zero-mode creation and annihilation operators, and the ground state, or one of the ground states, is precisely the one where also A annihilates the ground state, the A case annihilates the ground state, and the expectation value of the field phi in the ground state is 0. But of course, I can shift that value by acting with this charge. So I can construct, the charge is just A minus A dagger, the zero mode, then I can actually shift the value of the field by using the broken charge. Is that clear? Notice, interestingly enough, that if I look at the expectation value or the sandwich between the original vacuum and the one shifted, you get this particular quantity. And notice that, of course, this tells us that symmetry doesn't break infinite volume. There is always a non-trivial amplitude to go from pointing in this direction to pointing in that direction. And the interesting thing is that the amplitude depends on the volume of the box. Sorry, the surface value of the box. This space-time, d minus 2, is the volume of the space-time box. Of course, if you are looking at pions and the breaking of the usual chiral symmetry, and you are looking at something like this room, for all practical purposes, the symmetry is broken. Okay, because the lengths that appear here are microscopic. I mean, this is like I think it's clear. So when the volume goes to infinity, notice that this amplitude goes to 0, and as we learned in the usual presentation of Goldstone's theorem, the Hilbert spaces built on 0 or on chi are completely orthogonal. And any local operators will create states that are also orthogonal. So there's a fiction. When people say that there is vacuum degeneracy in infinite volume, it's kind of a fiction. Okay, and you can understand where the fiction comes from, except for 2 dimensions. In fact, in 2 dimensions, there's the famous Mermin-Wagner theorem, or Mermin-Wagner-Coleman theorem, which tells you that, in fact, in 2 dimensions, the quantum fluctuations of the field are so large that the symmetry is always restored, no matter how hard you try. And that's because of this d minus 2. This is just a number, 1/4, 0, or 1 or whatever. So there's always a finite amplitude to go from one particular ground state to another one, no matter what the volume is. Is it clear? I think this is the shortest explanation of Goldstone's theorem that contains all the ingredients. Now you can start beefing it up with more charges, more fields, whatever you like. Okay? This may be less familiar, but this is the canonical non-relativistic quantum field theory. See, it is written up there. If you actually vary the Lagrangian with respect to psi dagger, you get precisely the free Schrödinger equation for a particle of mass m. It can get simpler. However, there are some interesting hidden aspects if you haven't seen them before. This normally you say, there is a symmetry that is trivial. Change the phase of the field psi. Okay? This is the phase rotation. But you have much more, because I can shift psi by a constant and psi bar by another constant, and the Lagrangian changes by a total derivative. Therefore, there is a symmetry. Well, what you have is that the group of symmetries here is the homogeneous group in the plane. It's Euclidean, the group of Euclidean motions on a two-dimensional plane. Two translations and one rotation. And those are the charges. Rho1, Rho2, and Rho3 is the standard one that you associate to the conservation of probability, but the other two are also symmetries. And here we find something which is kind of remarkable. You compute, well, two things are remarkable. The first is that to quantize a non-relativistic field, we don't need to put antiparticles. The field psi, all you need is A of k. And the psi dagger will contain the A dagger of k. Of course, in the non-relativistic world, the CPT theorem doesn't exist. It doesn't hold. Particles can live without antiparticles. Okay? But furthermore, what we find is that, in fact, if I remove the volume, I mean, the naive group, which is the inhomogeneous group in two dimensions, contains here a zero. These are the two translations that commute. What happens is that when you quantize the system, if I put the H bar will appear there, but you find that you get what is called a central extension of the translation group. More importantly, if I look at the currents and the charges, A, here A is 1 and 2, sorry, I should have said that. Notice that the elementary excitation of the field psi interpolates between the field and the vacuum, and so does the current. Well, that's interesting, because that tells you that this is the signature for a Goldstone boson. And there is only one for two broken currents. Well, here we already break the standard rules in textbooks. Because normally you are told every broken symmetry has a single Goldstone boson. Well, here we have half of it. Two broken symmetries generate a single Goldstone boson. So you see that by being non-relativistic, in the most trivial example, we find something new. You don't find this in your quantum mechanics books. But you could find it, it's a trivial computation. So, you see, also notice that this is not a massless Goldstone boson, because the dispersion relation is this. It simply tells you that the energy is small when the momentum is small, like phonons. You don't have the same thing as E squared minus B squared is equal to M squared. So the notion of small excitations, or the notion of what is supposed to be a Goldstone mode, changes radically. And in fact, one of the reasons why Kibel, Hagen, and Guranik published their paper later, or after Higgs and after Agler and Brout, is because they were puzzled with this problem. They made the horrendous mistake of deciding how to generalize or how to restrict the relativistic case to the non-relativistic case. And they found that it was a mess. In fact, they wrote a paper with 120 pages that nobody knows about, where they were actually looking at what happens in the case of Bose-Einstein condensation, the case of superconductor and so on, and they wasted almost 6 or 7 months in trying to understand that particular thing. Until they decided to publish, well, they got so confused that they decided to publish the relativistic part. But unfortunately, they arrived too late. Anyway, that's really, sometimes history plays. There is a theorem that was proven a few years afterwards in 1973 by Chada and Nielsen, which tries to really explore this particular possibility. Okay? And the answer is the following, at least with some assumptions, again with some form of locality, which I'm not going to get into. But they found that, in fact, given a Lagrangian invariant under a given symmetry group G, dimension n, we can construct nether charges. And fields satisfy this condition. In other words, you have some fields, you have some charges, you have the expectation, you look at the commutator of phi and q, that simply means that the field phi is going to move under the symmetry. And you also want to make sure of is that these commutators or these variations acquire a vacuum expectation value. Otherwise you don't have a symmetry breaking. Well then, if this determinant is different from 0, so it has maximal rank, and you have some locality, what they found is that in fact, if translational invariance is maintained, the total number of broken charges is equal to N1 plus 2 N2. And these N1 and N2 are telling you simply that the energy of the low energy excitation of type 1 is odd in momentum. And the second excitation is the one where, in fact, the energy of the low energy excitation is even. There are some pathological examples where R could be bigger than 1. But let's forget about these pathological examples and fix R equal to 1. And then what you find that indeed is the two examples we had before. One associated to the energy going like the momentum, which could be relativistic, or it doesn't have to be. As I was saying, if you look at the phonon in the acoustic branch, well, low energy, it goes like P, it's the sign of P. Or you can have the non-relativistic case, like in the Free-Schrödinger equation, where what you find is that in fact the energy goes like P squared. Now, there's been plenty of work afterwards by some of these people here, Uralnik, Hagen, and Kilwald at the beginning, Lloyd Wheeler, Murayama, Browner, Watanabe, Nick Collins, many people who've been trying to explore, try to lower the assumptions made by Chada and Nielsen and try to see how far you can go into determining these things. And in a sense, you get some formulas, which I'm not going to abound too much on precisely under certain conditions. You can estimate the number of even Goldstone bosons or odd Goldstone bosons. The important thing is that the even Goldstone boson, N2, always, in a sense, you only need half of them for every Broca symmetry. Is it clear? I don't know, maybe you will all know these things, but then I can accelerate. Now, now we start considering, let's try to explore this structure in the relativistic context. I don't want to really get into the exploration of all these possibilities because it's kind of complicated. But something that was invented by Nicolis and Piazza, and they call it spontaneous symmetry probing. What I can do is I can try to look at, as I was saying, I have a theory which contains a given symmetry. What we can try to do is to break Lorentz invariance, but at the same time compensate it by rotating in the internal space. That's what you do, for example, when you look for topological solitons. You look for Q balls. In all this type of situation, what you have is that, in a sense, you're actually making sure that the Hamiltonian annihilates the vacuum when you are in an excited state, but somehow it is compensated always by rotating in symmetry space. In a sense, you are using the symmetry as a clock. Therefore, you're looking at that sector of the Hilbert space where the clock, which is time evolution, could be done by the original Hamiltonian or by the Chart density. Okay? That's what is called spontaneous symmetry probing. I'm probing a sector of the Hilbert space as though it was breaking Lorentz invariance, which it does. Any state that has non-zero energy breaks Lorentz invariance, and it should. But you're trying to do it in such a mild way that breaking can be compensated by rotating in space. Anyway, we start with some formulas. I'm not going to dwell too much on them. The important thing is that if you do this and try to analyze the consequences in this simple example, what you find is that the description of these states, even if you have Hamiltonian, like a Mexican hat or whatever, always has, or generically has, this type of structure. You can always find, at least in the example we've been looking at, that for that sector of the Hilbert space, the ground state breaks the symmetry, as it should, because we're trying to look at the Hamiltonian. But fortunately, it is done in such a way that somehow you can expand and understand this theory as though you were looking at a theory that breaks the symmetry. And precisely what happens is that, of course, the canonical conjugate variable to the charge, let me call it chi, the angle or the field phi, is always rotating in time. So you're actually looking at configurations of your field, like the things that depend on t, that are actually rotating in space. Okay? It's like having angular momentum. You try to look at the sector of highest angular momentum or the Ripper atoms. This is one way of doing it. And actually, it gives you an effective field theory associated to the low energy excitations around this particular ground state. Now it's interesting because we've actually broken Lorentz invariance, but in a way that is controllable. You can still control scaling variance, translation invariance. We can control some part of rotation invariance, and we can also actually have some expansion parameters that I'll look at it later. Now you could actually be more brutal and look for solutions which are not only time dependent, but they could also be space dependent. These are called the striped phases that appear in some context, but I'm not going to get into this. I mean, the one I'm saying that if you look at the non-relativistic theory, in generality, then you can actually select ground states that are not just time dependent because they rotate in time, but also that they have stripes. So they have, it's like domains. You look at a ferromagnet, they have domains. So you could imagine, let's try to look at a theory where you get the develop domains and see what are the Lorentz excitations. So there's a huge phenomenology you can make, but this time I'm just going to concentrate on this. Well, if you do it not classically, but you do it quantum mechanically, then essentially what you're trying to do is the following. I want to look at the minimum of the Hamiltonian, the lowest energy state of the Hamiltonian, with states that are normalizable, VV equal 1, and where the charge density is constant. Okay? Now, you sit down and do a little mathematics, what you find is this is precisely the states that are described in the previous slide, but where the rotation number is fixed. In other words, the chemical potential mu is fixed. Okay? And as I was trying to say, I'm not going to get into details, but we'll see the details later on. This automatically implements this generalized version of Goldstone's theorem. So this is the problem we're trying to solve. The Hamiltonian is something that we don't know very well if we're in one of these quantum theories that are at strong coupling. But as I'll try to show you later, if we are looking at these states, or oscillations or operators in this fixed charge Hilbert space, we can in fact do some interesting computations. So the type of model theory we can be looking at, this is a kind of heuristic, to look at a three-dimensional theory, which is written there. It has what is called ON invariance, that could be just O2, and I'm looking at a box that is a sphere. Well, when the box is a sphere, I can also include technically the second term in the Lagrangian, which is just the scalar curvature, takes into account the curvature of the sphere, which is like a space-time or a space-dependent mass. Okay? So my space-time now is up to a sphere times time. Okay? Of course, the type of arguments I'm going to be doing now are totally heuristic, because when you go close, this theory is scale invariant. But when you go close to the scale invariant of the fixed point, this theory is not perturbative. So I'm going to be doing heuristics because I'm going to compute as though I didn't know that. Okay? And we'll see how far you can get, and you can get some interesting results. Well, this is where the core details come, to show you that we do some computations, but anyway, the only thing that you should notice is that when you look at the low energy configurations, the one that give you the ground state, in this simple example, which is, say, if you look at a theory that has ON symmetry, rotations in n space, this is what is called a vector in that particular space. And with a vector, you can only construct one invariant, which is its modulus. Now, if I'm looking at a theory that is not just a vector, but a matrix, then I could have many more invariants, and this would actually be far more complex. In this case, of course, what happens is that these ground states are associated to a few of the fields rotating with the same frequency, and the other set to zero. Okay? Anyway, so you do all these things, you suffer a little, and then this is the end result. The end result is that, in fact, if we want to fix k charges in the Cartan subalgebra of O to n, then of course you have some kind of a partial symmetry breaking. By using symmetry, you can show, but the Hamiltonian takes this form, which is, with the corresponding chemical potential that is fixed by the rotation of the system, and then you have the charge divided by the volume of the corresponding sphere. And again, by using the UN symmetry, you can rotate the vacuum expectation value to this very simple form. So now you can actually analyze the spectrum. I'll just go directly there. Well, and I'll come back to for something. The important thing is that when you do semi-classical analysis for this theory, no matter what the potential is, okay, this is the key to make some model results universal. What you find is that there is a single relativistic Goldstone boson, but not with speed equal to 1, by the speed of light. It's speed equal to 1 over square root of 2. Good, you don't violate causality. In other words, there is a Goldstone boson of type 1, where the frequency or the energy is linear in the momentum, and all the others are either non-relativistic Goldstones, you have k minus 1, and all the other modes are massive and can be integrated out. Okay? Now, the other important thing that I'm not going to get into great detail, if I can go back here, is that if we start perturbing around the ground state, apart from the Goldstone mode, you can actually show that any coupling constant you may have is renormalized into something which is that coupling constant divided by a power of the total charge. In other words, as the charge becomes larger and larger, you can make the coupling as small as you like. I mean, this is the key to the whole game. If this didn't happen, what I will tell you now is nonsense. So this is like the 1/n expansion in the number of colors on the number of components of a field. Sometimes you don't have an expansion in couplings, but you can have an expansion in these additional parameters. This is the nice thing about this large charge sector. In essentially going to the WKV approximation. WKV, essentially everything is a bicassical. The corrections are very well controlled, no matter how strongly coupled your quantum mechanical system is. Okay? But this is just a technical detail that is important. Because now, you can actually compare the type of things that we do normally in conformal field theories. You know, we look at the corresponding fixed point, which is associated to these small excitations that are quasi-relativistic. And, well, when you look at, you have theories that are scale invariant. It seems, although again, there are different proofs, which some of them are false, some of them are not, but somehow it seems that frequently, when you have scale invariance, you also have conformal invariance. In other words, any transformation on your geometry that preserves angles. Okay? Again, like in the Goldstone theorem and similar things, you know, there are many caveats and there are many things hidden in these proofs. But at least in this context, if you look just simply at scale invariance, you can actually construct a theory either on the plane, say we look at the three-dimensional theory, or I can simply compactify conformally 2 dimensions into S2 times R. The difference is that in the case that we're looking at this conformal theory, it's scale invariant on the plane, then what makes sense to be computed in the quantum field theory are the dimensions of the fields. Because that's the way that fields scale. You know, a field scales into phi of lambda x, goes into lambda to the dimension of the field, times phi of x. Okay, this is the way that the scale transformation acts. So you are computing what is called anomalous dimensions. If you do this conformal transformation, then you're looking at time to be kind of a logarithm. And in a sense, in this quantization of the cylinder, you're looking at energies of this particular system. And the relation between the two is given here. The dimension is just the size of the radius of the sphere times the energy. Well, in that theory that I was describing, this is the general form of the dimension as a function of the charge. The first 2 coefficients, of course, depend too much on the coupling constants. We know that they have to be like this by general dimensional analysis. Okay? However, the coefficient that comes, the third coefficient, that is coefficient of q to the power 0, this is the coefficient that is based on the Casimir energy, or the Casimir contribution of the massless Goldstone boson. And it is independent of its couplings. This is a universal number. This is the one you have to check with Monte Carlo simulations. So that's it. You know, this 0.093 and so on counts precisely for this particular Goldstone boson. And this is a contribution that is independent of the coupling constants in this particular theory. Okay? I'm saying here exactly the same thing. And let me see just what I'll just tell you. You know, if we compare, for example, with some of the computations that have been done using Monte Carlos for this type of O2 theory, as I say, the first 2 coefficients, C3½ and C1½ depend very much on the details of the theory. What we found, heuristically, is that our computations in naive perturbation theory and the numerics satisfy this particular rule. We have no idea if this is an accident or there is something to be understood there. But it's kind of remarkable that you have this formula. The boxes correspond to precisely, you know, the anomalous dimensions that we've been computing, and this is the fixed charge. These boxes correspond to the Monte Carlo computation done by people here. And notice that somehow the prediction from that particular formula is remarkable. Of course, this is only one prediction. The only prediction we have here is the 0.0937. Because the C3 and the C1 we fit with the Monte Carlo. And interestingly enough, that constant in this computation is 0.09 plus or minus 0.05. Well, not so good, but not so bad either. Even the little work we put in. We can also consider the case, not of O2, we can look at ON. And here you have, O2, O3, O4, and O5. And remarkably enough, the formula, because the existence of this extra Goldstone boson is independent of N, of the ON, or the Wilson-Fisher fixed point. So interestingly enough, you can see that again, the fit is kind of remarkable. And the number, that is the Q-independent term, is again the universal linear Goldstone boson. So I think there's much to be understood in this type of arguments. There's much to be understood in this type of computations. But there's been a lot of people now getting into this type of work. And hopefully, in the next few years, we'll be able to have some kind of a hybrid way of understanding the large Q and the large coupling expansion in really trying to delineate what is the space of strongly coupled theories. Now, I think that as a summary, there's something interesting. Today is the 100th anniversary of the not today, but this year, the 100th anniversary of the publication of Nether's paper. It's also the 50th anniversary of the Veneziano amplitude. I'm not sure if it's a coincidence. But anyway, this is kind of interesting because, this is a dictionary paper that she wrote, how to relate continuous symmetries, or continuous currents, or conserved currents, to symmetries. I mean, this is something which is a remarkable and profound result. And it still, as you can see, has not yielded all its secrets. We're still understanding how these symmetries can be realized in this particular context. Now, as I was trying just to summarize, this hybrid that we've built between relativistic field theories and relativistic field theories, thanks to working in sectors of large but fixed charge, is actually yielding some interesting results or yielding some interesting alternatives to bootstrap, to lattice computations, and somehow it can be put in our bag of tools to understand theories that are strongly coupled in the infrared or the ultraviolet fixed point. So as I was saying, there's a number of papers after our work, also from Jaferis, Boedo, Carmo, and many others, who really keep exploring this particular thing. Anyway, I think I'll finish here. Thank you. I ended early so that I could save you some of the formulas. I didn't want to torture you.
Question?
I was told that today I should not ask questions.
You should.
I think you gave a very good motivation for generating non-local interactions, true?
Yeah, absolutely.
Yes. My point is that once you have a non-local interaction, even in the context of a quantum field theory, there is no guarantee of the CPT theory.
Absolutely.
Okay, no guarantee.
Yep.
There is a matter of necessary and sufficient conditions. That means it would be interesting to explore whether these non-local components are able to generate CPT violation. You know that experimentally, in particular these days with this anti-hydrogen test and so on antimatter, the tests of CPT are extremely precise, reaching the scales of the Planck scale. That means that I think this is a very good way looking for the violation of CPT. By the way, I always repeat that at the level of quantum mechanics, there is nothing against the violation of CPT.
No, absolutely not.
It's only when you go to quantum field theory with local interaction. Okay? And I think this is a very good way looking for CPT violation of exploring the possibilities offered by these vacuum properties in the quantum gravity effects. I don't know, I would like to...
No, I agree with you. I think that, for example, doing a general, if you look at effective field theories in the non-relativistic context, most of it remains to be done. Because that's precisely addressing your question. See, in the type of theory we are doing, we are kind of lazy, because we start with a theory that is relativistic from the beginning and local. So it's only when we restrict ourselves to the sector where the charge is very large that antiparticles decouple. So in a sense, this effect of the average charge somehow decouples particles and antiparticles. You only get light, those that attract the same charge, and the others that are repulsive.
Effective interaction with momentum-dependent depth.
Exactly.
Non-local.
Exactly.
Non-local depth.
Exactly. That's the way you actually decouple particles from antiparticles. Those that have light charge to the background charge will get a very large mass, and the other ones are the ones that are going to give you the small excitations. But it's interesting, as you were saying, that you could think about this not in this particular context, but more generally, what is the general way of doing effective field theory for ordinary Lagrangians or Hamiltonians, where you only preserve, say, translational invariance and rotational invariance. And then there's a whole world that opens. Some people have been trying to look this into Lorentz invariant violations and so on, but the CPT theorem, for example, or even time reversal invariance, when it breaks, there are many example time condensed matter which do violate time reversal.
Yeah.
So, I mean...
but if in condensed matter you have a medium.
Right, precisely. No, but I think
medium that breaks in that case.
It's a very good question, and I think this remains to be done.
Okay, thank you.
I think theories can ask questions too.
More questions?
There's a question there.
Yeah, because that's something that I'm not sure I understood.
Wait.
So at the beginning you start talking about the Coleman-Mandula theorem.
No, only the Coleman theorem, not Coleman-Mandula. No Mandula here.
Okay, so what happens that you cannot apply this theorem when you're doing this?
To Coleman-Mandula. No, Coleman-Mandula, Coleman-Mandula is something that, again, it also breaks in the non-relativistic case, because it's too weak. So, Coleman-Mandula has certain assumptions that are too strong, and in fact, the theorem is, there are many counterexamples. That's the bad thing about proving theorems in physics. You should never prove theorems in physics, because most of the time, the interesting cases are the counterexamples. So, Coleman-Mandula missed supersymmetry, they missed Yangians, they missed the integrability of unequal 4, because somehow to prove theorems in physics, well, I'm trying to be unfair, quantum field theory is far too complicated. So it's very difficult to pose theorems with the same level of rigor as in mathematics. So every theorem normally contains so many hidden assumptions that when you look at them more carefully, it's very easy to break them. So this theorem of Coleman, essentially, the reason why it works, believe it or not, is because locality and relativistic invariance guarantees that for every particle there's an antiparticle. So any local operator that annihilates the vacuum will have always a part that has creation operators and annihilation operators. So the annihilation operators always remove the vacuum, but the creation operator will not. So it's precisely what Pepe was pointing out, is that it is precisely these are real theorems so far. Okay? Locality and relativistic invariance forces you to have this. It's called the Johnson-Freiderburg theorem. And that's why Coleman theorem works. Coleman-Mandula has to do with more assumptions again about how to describe the asymptotic states and what is the structure of the S matrix. And those are too strong. For example, a fermionic charge does not satisfy clustering because the values of fermionic charges in space-like separated regions anti-commute. And then the theorem is gone.
Maybe it's a naive question, but in the last slide, you were showing how to mapping a sphere in a cylinder.
Yes.
And you can connect the anomalous dimension
Yes.
with the radius of the sphere and the energy.
Yes, yeah.
And in the later slide, you show how the anomalous dimension is connected with a fixed charge.
Yes.
So I was wondering how the energy and the sphere interplays inside the fixed charge of the slide after.
It's the formula that I had before. It's just linear. It's a very this of course. The good point is that I'm assuming scale invariance.
So you can always do it.
Yes, if I don't have scale invariance, the formula has many corrections. But in the case that you have scale invariance, the general formula is this one. Let's see. Where is it? Here. D is equal to R naught times E. Makes sense because you have to get something that is dimensionless, which is the anomalous dimension. So you have a given energy, the only universal number that you have that is not renormalized is 1 over R, or R naught. which are dimensions of 1 of the energy. Okay, but if you did not have scaling variance, there are corrections to this that will look like 1 over E and all kinds of things. Everything is clear, I see. Happy.